with the same level of health that you can, okay, starting from a very simple, very basic thing, diffusion algebra point, which is you can gradually build up by a downloading process. You can gradually build up to more advanced stuff. So this is a very either 1, 0 or 0, 1. Right? This is the even dimensional subalgebra of both of these, right? So one of these is the complex numbers. The other is the hyperbolic numbers. If you use this kind of better page for the hyperbolic numbers.
Yes.
Okay. You can actually show that this is like having 2 copies of R. It's also called sometimes split complex numbers. And the way to make this separation is exactly using this idempotence. So these idempotence we're going to play an important role each time you have non-trivial metric. I mean non-Euclidean metric, non-trivial signature of the metric. So it's a good place to track this idea from the very basic context. You have 2 generators. One is the identity which you have. Actually, it's not a generator. It's the identity element of the algebra. You have one generator which, how do you call it? Is 0? No, I don't know. There's only one of them, so E. So you have one vector because the space is one dimensional, and it squares to 1. Okay? There's nothing more. You have numbers like A plus EP, which are similar to the complex numbers, except that we have 0 divisors here, and those 0 divisors, sorry that I'm repeating what Professor Gonzalez explained. The reason is that I want to have it here written in the simple context because it will make a more complicated setting. So it is quite obvious what we call this tau plus minus. I think I'm using the notation of Professor Barnes. If you call this idempotence tau, okay, first of all, what does an idempotence mean? I think it has been it has been said already. But the thing is that when you multiply the 2, you get 0. Yes. That's right. That's why there's 0 divisors. When this affects words like this, it's good to explain. Because when you multiply 2 non-zero numbers, you get 0, which you don't see much of this in the algebra of 0 numbers. You don't see actually any of this. And these things square to 1. Okay. So for those of you who are into physics, this pretty much resembles the composition of the wave potential, etc. Potential into retarded potential. What was the advancing retarded potential, right? Advancing retarded potential. This is the same construction, but it's easier to see in this setting in which you can easily relatively easy to draw pictures. Because this is something like the complex plane, but now we call it the hyperbolic plane for some reason. Or some people use this notation. This is dual to the complex number, which means dual in what sense? It looks like in algebra. Okay. So something that's close to -1 in the complex plane, now close to +1. And you have these regions, so you have a causality light cone, like special relativity. You cannot easily cross this boundary. You cannot cross it with legal methods, so to say. This picture is going to reappear, but in a more complicated setting in which you have more dimensions. So let's just keep following this track. So each algebra here, each more dimensional algebra in this chain is embedded as even subalgebra. So it's a fixed point of some involution. Actually, this is called the principal involution, the one which turns the sign of each vector. Right? These things come from vectors. Okay? So if you just change the sign of every vector, what remains fixed is the subalgebra consisting of even braid elements. Right? So if you keep on, okay, this is going to be a tree, no? This is going to be a tree because, for example, the complex numbers can be embedded in here. 0, 2, which is the coterminus. Okay. Professor Marcus is not here, so I will stop speaking about coterminus. I will use this word. Okay. So this is also embedded in 1, 1 and 2, 0 as we just learned. 1, 1 and 2, 0 is the same thing. They're isomorphic as the algebra. So, otherwise I would need another arrow. Anyway, when we draw here, what do we have? What about this one? Okay, complex numbers are relatively easy. We're all familiar with them, right? So we know how to go from there. There are other ways. Of course, we have the bicomplex numbers, so-called testings or duplex numbers. They have become fancy again in recent years, again in relation to special relativity. But those numbers, they are not really different algebra. They are complex different algebra. So I'm going to write it here. Where can you go from here? These are the hyperbolic numbers. Wait a second. Is that correct? Isn't this supposed to be here? Okay. And you can continue. So, this is embedded in the space-time algebra. So pick the metric you like, you prefer. 1 plus 3 minuses or 1 minus 2 pluses. The spaces are isomorphic, right? The default algebras are not. So that's a problem learned in physics in relation to my Rana spin-off.
The physical advantage of the second is that the matrix representation can be real.
It has real resistance.
And the other is pure imaginary, artificial realities.
So this one can be written as
with the different mixing. So this can be written as 4 by
so it says move to the matrix algebra for the other one is well, this one is 2 by 2 quaternion, right? Oops. Sorry, I didn't estimate to go this far. I think it's 2 by 2 quaternion.
The representation is the same, but instead of real numbers, imaginary numbers. The representation.
Yes.
Both and imaginary. The habit is the same, that is.
Imaginary, but not.
Imaginary of complex numbers, imaginary.
This sounds suspicious now. You know, very imaginary.
Okay. This is
Okay, so we expect this type of construction is inherited from the hyperbolic plane. Once Professor Gonzalez used the hyperbolic plane to generate the Clifford algebra, but also the Clifford algebra at the line, the real line, is actually the algebra of the hyperbolic plane. So from two different perspectives, it's the same object, but it's seen from two different perspectives. So I mean the hyperbolic numbers of the strict complex numbers have this property. The first time we saw these idempods that give you the decomposition of the target, what is it? X plus ct. We have such decomposition into a retarded and accelerating advanced potential. What's it called? Sorry. Advancing potential. Sorry. Okay. So we're expecting to see the same thing. Let's see how these algebras are constructed. So, which one should we pick? 1 plus 3 minus 6 or the other one? Doesn't matter that much. Let's start with the first one. Okay, so we have gamma 0 squared equals plus 1, and gamma k equals minus 1. Okay, originally these are the direct matrices that participate in the film. This is one of the reasons that the Clifford algebra has been reborn, so to say. And unfortunately, physicists still learn about Clifford algebra, or at least hear about Clifford algebra for the first time in this awful way. Given a set of matrices, prove that they satisfy a given multiplication rule. This is repelling, so at least repelling. Okay, so k equals 1, 2, 3. Gamma 0. No, I use 0 the way you use it for the time. But also we have 1 which is 1 of the algebra. So what basis can we have? We have the geometric element, we have gamma 0, gamma 1, gamma 2, and gamma 3. Those are the grade 1 elements. Then you have gamma 0, gamma 1. Okay, I'm going to maybe I should gamma 0, 1, gamma 0, 2, gamma 0, 3. And then gamma 1, 2, gamma 3, 3. Those are the grade 2 elements. Sorry, this is 1, this is 2. Okay, how many many grade 3 elements are we going to have? Well, it's always, if n is the dimension of the space, and k is the grade of the corresponding element, how should I write it? Yeah, okay. The corresponding subspace of monomers. So what is the dimension? How many generators do we have of grade k in dimension n? It's pretty combinatorial because you can reorder this combination. If you have gamma 1, 2, this is obviously gamma 2, 1. The same thing modular factor. So here we have our dimension is 4, right? So for grade 1 we have 4. For grade 2 we have what? 6, yeah. We already have one. For grade 3 it's the same as much as we have here, right? So we have 4. Let's try to write it.
Pascal
Yeah, sure. Also, postgrad, we talk about this tomorrow. 0, 1, 0, 2. Sorry. 0, 1, 2. 0, 1, 3. 0, 2, 2. No, you can't have this. No, you cannot have the same units twice. Okay, just to be sure I don't miss this, we're going to put 1, 2, 3. What's missing here? 0, 2, 3.
0, 2, 3.
Yeah. So you have vectors, you have bad vectors, and you need to have, of course, 3 vectors, and you have one more element which is the true scalar, which is gamma 0, 1, 2, 3. This is the product of the grams. Sorry?
Scalar and true scalar. How you define true scalar? How you define scalar? How you define scalar?
Scalar is every multiple of the, so it's a one-dimensional space of the identity of the algebra. Every multiple, you take numbers from the number of fields as coefficients. Okay? So it's a mod.
Scalar is an element of unital ring. Scalar.
Okay. It is ring, but it's even better than ring because it's a field, no?
But you cannot find this definition in no one book of university mathematics and physics. They never have definition of scalars.
Yes.
Do you found? No. Only this school of Vargas has definition which I gave now, that this is element of the ring.
Of the ring.
Yes, every scalar must be ring of the ring. The product of two scalars must be against scalar. Sum of scalars must be against scalar. This is very important.
Okay, it is a ring, but usually we take a scalar to reside in a field, no? Because we want commutativity.
Field is particular scalar where the multiplication is a group.
Yeah. It's a particular case.
Classification of ring, but this is not so important.
Yeah.
Conceptual definition of scalars is very important. This is the key idea.
Okay, thank you. So I'm not. Okay, so thank you for this opinion. But at the moment, I I'm using only the particular case of field, because in our case we consider algebra over the reals, not algebra over the reals, but over the complex numbers. So in both cases, it might be not the most general definition, we're dealing with fields now. So, what about the pseudoscalar? Why is this a pseudoscalar? It might not commute with the other elements. So, this is the center of the algebra. This is the center. This thing might be also the center, as we saw in the case of three-dimensional algebra. The pseudoscalar, or the volume element, some people, it commutes with everything else. As in the center, it may also anti-commute. Okay? So in other commutes, or anti-commute with every element of the algebra. Also, it's equal to either plus or minus 1. Let's find out what happens in our case. Okay? Let's find I squared. Sorry, simple exercises like this may be extremely boring for specialists, but they're good for people who have this stuff. So, our claim is that this is either plus or minus 1, because we have elements that square to either plus or minus 1. They are anti-commute, so they just need to count how many minuses are there. Okay. So this has to go here, right? 1, 2, 3 minus. So we have a minus. 3 steps. Then you have 1, 2 steps. Okay. So we have 3 plus 2. Okay. Now we have one more. So these 2 don't exist now. So we have 1. Okay. And finally you have one more. Okay. So this is 0 because this one is already they annihilate each other, right? So something proportional to the identical. So we have 1 plus 2 plus 3. Okay? Actually, but then you need to count the number. You need to count the number of minuses because this thing squared gives you plus 1. Down 0. Squared gives you plus 1, but there are 3 minuses that you need to take into account. So you can do the same trick for every Clifford algebra of the reals and see that this is equal to minus 1 to the power so this is the number, this is the sum of this geometric integration, plus q. The number of minuses you get from the signature of the metric. Okay? This thing we will see shortly in relation to the same formula in relation to the so-called Hodge duality, which turns out to be equivalent to multiplication, modulo sign. It's equivalent to multiplication with the pseudoscalar. So what it makes is that it takes grade k elements to grade n minus k elements. This is the famous Hodge duality in Grassmann algebra. Written here only as a multiplication. So let's see. For example, little bit in advance, but it's important for the physical implementations I'm going to discuss. So, if you want to take a vector and you multiply with r. Okay, some people multiply on the left, others on the right. Some people multiply with the inverse on the right. They're all the same, with, well, up to a sign. So I'm going to multiply on the right. So that is this thing goes here, which means you need to change the sign once. Okay? And it squares to -1, so you change the sign twice, and you end up with gamma 0, gamma 3, sorry, gamma 2, gamma 3. So you begin with the 1 vector, and you end up with a 3 vector, which is 4 minus 1. Yeah?
That's how
duality works. Okay, so again we have a pseudoscalar, our monomial of Kai's grade is it squares to -1. In this case, we have -1 to the power of 4 plus the index of the metric is 3. So you have 6 plus 3 equals 9, which is -1. Okay? So you have I squared equals to -1, and it commutes with everything. Okay? So it commutes with everything. So again, you have something like the imaginary graph. Now, to make things a little simpler, let's just take the fixed points of the principal evolution, that is the so-called even rate algebra. That we give you one figure. This is the space algebra. Why do we do this object? Because it gives you the group of isometries. Not the whole group, the isometries of the vector space, not of the affine space. So to say, the homogeneous group of isometries, the Lorentz group. Okay, so it actually gives the proper Lorentz group. Let's see how. Well, as we said, how should we do all elements here? Sine equals no, Lorentz. So L times psi times L to the -1 plus psi. So if you restrict to elements of the Clifford algebra, how should we call it? It's called the Lipschitz group or the Clifford group. I'm going to take only invertible elements from the Clifford algebra. I want to give the notion of pin and spin groups.
What is Xi
is an element of Xi is a one vector. It's an element of the vector space. It's that.
It is vector?
Yes.
Xi is vector.
Yes. Xi is a Lorentz. The vector of Minkowski space. And we're going to perform geometric operations like Ramon suggested with a 3-dimensional space, but now we're going to do this in 4-dimensional space-time. So the very same idea. We just need to make sure that the inverse exist because it's not always, we have zero devices and so on. It's not always guaranteed. So what we're going to do is to restrict to invertible elements. How should I call this? This is the easiest reaction. Here, across here. Okay? So this means all elements that have to inverse. This is a group. Obviously, this is a group. If you can reverse this part here, we have a group from the different type. So the evolution. Now, how does it act? If you take L to be a vector, this gives you reflection. If you take L to be representative of the even dimensional subgroup, this gives you rotation, so pseudo rotation in this case. So this is a composition of even number of rotations. Even number of reflections. So, first of all, usually, if we take only conjugation here, we need also to make sure L has unit length. Okay? But by taking the inverse, this problem takes care of itself. This problem takes care of itself. Sure. If you take we do one more restriction to get to the Lorentz group, the group of isometries spacetime. We get one more restriction. Now, this is that L has even grade. Now, I'm going to write this is the even grade elements plus something else. Just the odd grade elements, obviously. But this is a subgroup. Because when you compose odd grade elements, you might get even grade elements, but the other way around is not possible. So this is a subgroup, and we call this subgroup spin. Spin is determined by the signature of the matrix. So, in conjugation, gives you actually projection of this group onto the Lorentz group, because there is a kernel, there is elements like this close the group spin, but when you perform this operation conjugation, there is a kernel here, because if you change the sign of L here and here, this cancels. Okay? So plus or minus goes to the same place. So the kernel stays 2. Okay? So the projection onto the Lorentz group is because of this matrix, so to say, quadratic. It's not quadratic, of course, but it's quadratic in terms of changing the sign. Okay, so to get the Lorentz group from scratch, one doesn't actually need the whole space-time algebra. One only needs the even component of the space-time algebra. Okay? Actually, this means what is the even component again? Even component is the space algebra. So if you take non-zero, sorry, if you take invertible elements here, you already have the Lorentz group pretty straightforward. And this is, as we saw before lunch, this could be written as a complexification of the ring of quaternions. What does this complexification mean? Well, we have a quaternions, for example, Q, I don't know, P and Q. This is real algebra. I'm going to introduce an imaginary unit. P plus IQ will belong to the complexified So to get from the group of rotations, the Lorentz group is a simple complexification of much. So if you're interested in isomorphism, you're going to come four dimensional space. As Professor Lara has mentioned many times, the Lorentz group does not apply relativities. The other way around is super. You may have the Lorentz group as a Young's group of the unit sphere, so you may not unit whatever sphere, but you may start from conformal geometry to two-dimensional sphere, and you'll get not the whole Lorentz group, but the one you need, the one that preserves the causal structure, so-called proper Lorentz group. So this is one option. Another option is by complexification of quaternions. Sorry, I keep writing with that. This means, of course, unit quaternions project to the Lie group S of T, and complexified quaternions project to the Lorentz group, the proper Lorentz. So it's another way of obtaining for example, Maxwell's equations or Lorentz transformations from just considering not only the even subalgebra of the plane, sorry, of space, but the whole algebra, the whole Clifford algebra. So, maybe I should start at some point. I think I'm confusing people more than making things clear. Should I just stop here or clarify? What do you think in terms of time? How much time do you have? How much time do you need from now?
How do you
Okay, maybe just 5 more minutes. 5 more minutes. One option is to make this illustration explicit. If someone would be interested in that. Another option is for me to shut up and more natural way. Otherwise, if you come up with Minkowski space first, then you have to come up with a reason why you want to throw out the group elements that don't preserve causality, the causal structure. Yeah? You need to come up with stuff like the principle of relativity, about the maximum of the maximum velocity of light. It is a postulate that one doesn't need to if one gets the proper group from the very beginning. Sorry, did I stick to the plan? Should I explain?
Do what do you want?